Yeah, okay, let's start. Today I will talk about the alternating series test and the ratio test and root test, and then I combine all of them and talk about a strategy to find a good method to determine if a series is convergent or divergent. Okay, so let's start from the alternating series. So what's the alternating series? The alternating series is a series like, okay, so this is a notation of the series -1 to n minus 1 bn, and then I mean on this alternating series for each terms is like b1 is positive, and then the second term is negative, and then the third term is positive, and yeah, and so on. So we call this series is alternating series. So here is the alternating series test. So this test only work on the series like that. So if this series satisfies these two conditions, so the first one is the bn plus 1 is less than bn, I mean for all n, and then the second one, I mean the first one is the series is decreasing. I mean we just ignore the -1 to the n minus 1. And the second one, we need the limit of this bn, it goes to 0. And then we can say this alternating series converge. So, and then this one converge. Okay, so I will give you two examples to apply the alternating series test. So the first one is if we are given a series, it's a summation of -1 to the n times 1 over 4n plus 5. Okay, and then I apply the alternating series test to check the convergence of this series. So the first one, I check the first condition. I mean the next term, it should be, I mean the bn should be always decreasing. So I write down the bn plus 1 and bn first. So it's 1 over 4. Okay, so I got bn plus 1 is 1 over 4 times n plus 1 plus 5. So which is 1 over 4n plus 9. And then for the bn is 1 over 4n plus 5. Okay, so we can see, we can compare the denominator here. So 4n plus 9 is greater than 4n plus 5. And also these two denominators are both positive. So we can say bn plus 1 is less than bn. Okay, so which means this series satisfies first condition. And then we go to the second condition. So the second condition is the limit of bn goes to 0. So I take the limit of 1 over 4n plus 5. Yeah, because the denominator goes to infinity and the top is a constant, so it means bn goes to 0. So this series satisfies these two conditions. And also it's an alternating series because it has a -1 to the n. So I mean it's positive, negative, positive, negative. So which means this series is converge. Okay, so this series is converge by alternating series test. Okay, so one more example on alternating series test. Okay, so the second example is we get an alternating series like the summation of -1 to the n times 3n over, so for example, 4n squared plus 5. Okay, uh, so because it's an alternating series, so we just check this condition to see if it's converge. Okay, so the first one, I think the second one is the easier one because I can take a limit of n, 3n over 4n squared plus 5. And we can see when n goes to infinity, 4n squared is dominant on the denominator. So, for this limit, it's like, you can apply the L'Hopital's rule. You will get 3 over like 8n plus 5. So, which means the limit goes to 0. But how about the first condition? How to prove that the Bn here is always decreasing for any n? So, do you remember I'm showing do you remember an example I showed to you? So, like the series is like a function, and it's only defined on the integer point. So we can write this Bn as a function of n. So like Fn is a function of n, which is 3n over 4n squared plus 5. So if we can show this function is decreasing for any positive number, and then we can say this Bn is decreasing. If we know the Fn is that, and then f prime n is always less than 0, so it means it's decreasing for positive n, and which means fn plus 1 is always less or equals to fn. Okay, so we follow this idea and find the derivative of the fn here. So I find the derivative by quotient rule. So for denominator, we don't have to consider the denominator because it's always a square, so it's positive. So the derivative of the top, 3 times 4n squared plus 5 minus I think it's 3n times, so it's 8. So it's 8n. Yeah, so it's 8n on the bottom. So I simplify it, and then I get 4n squared plus 5 squared. And for the top is negative 12n squared, and then plus 15. Okay, so we can see we need to determine the sign of the top. So if we know n is greater than 2, greater or equals to 2, we will have the n squared is greater or equals to 4, which means which means the top is always negative. You can plug in 4 and then you get the top is less than 0. So which means the f prime n is always less than 0 for any n is greater or equals to 2. Okay, so which means for any n we have the so for any n we have n plus 1 is less than fn. For n is greater or equals to 2. Yeah, because convergence or divergence are the property of a series, near the infinity. So we can just drop some finite term before. So in this case, I dropped the n is 1. So I just dropped the first term. and then consider the convergence for the rest terms. So, okay, so I finally got this series satisfied both of these conditions for alternating series test. So which means this series is converged by alternating series test. Okay, so let's go to the next topic. Okay, so I would like to introduce the absolute convergence first. So what's the absolute convergence? So the absolute convergence means the summation of an is converged. Okay, so is there a series that is there a absolute is there an absolute converged series but not converge? I mean, the summation of an converge, but the summation of an is diverge. Yes. So for example, we can write down the series. I mean, this alternating series, like -1 to the n times 1 over n from 1 to infinity. So, no, I think it should be absolute converge but not converge. This one is, but this one is converge. Okay, so for example, in this case, we know the absolute value of the series is the sum of 1 over n, which is a nature series, and then this one is diverge. And then, but from the alternating series test, we know the limit of 1 over n, yeah, it goes to 0. And also we know the 1 over n plus 1 is always less than 1 over n. So which means the series is decreasing. I mean for 1 over n. So by the alternating series test, so this series is converged, but its absolute value is diverged. Okay, so from this example, we can see the absolute convergence is stronger than just convergence. Okay, so this is what you should know about the absolute convergence. Okay, so let's go to the ratio test. Okay, so ratio test. So the ratio test is we need to find the ratio of n plus 1 term to the nth term. And then if this limit it goes to some constant, if this constant is less than 1, and then we can say this series is absolute converge. And then if this constant is greater than 1, we can say this is divergent. And then if this constant is equals to 1, so we cannot draw the conclusion from the ratio test. Okay, so this ratio test comes from I mean, this ratio test is like it's like a comparison to it's like comparing this series to a geometric series. Yeah, but we can use this ratio test directly. Okay, so some example. So we can use the ratio test to determine the this series, the convergence of this series. Okay, so it's the summation of k from 1 to infinity, k times e to the negative k. Okay, so here we write down the ak first. So the ak is k times e to the negative k. Okay, and then we find the ratio uh, of n plus 1 term to nth term. So I find the ratio first. So I find the limit of the ratio. So a n plus 1 over a n. So this one is the absolute value of, so for top is n plus 1 times e to a negative n plus 1. And then for bottom it's n times e to the negative n. Okay, so I can just distribute the limit inside. So it's limit, so I've split this function inside the absolute value. So I take limit for the first piece, and then take a limit for the second. So I can simplify them. So this one is e to a negative n plus 1 over e to a negative n, which is e. Okay, I mean we apply some rules of finding the limit, and then take a limit for n goes to infinity. So this one goes to 1, and then this one goes to e. So we get the ratio is e. So e is a constant, is 2.71 and so on. So I mean this ratio e is greater than 1. So no, sorry. I think this one is e to a negative n plus 1. So we will get e to a negative 1. So the final answer is e to a negative 1. And then e to the negative 1 is, because we know e is like 2.71, so it's 1 over 2.71. So we know this ratio is less than 1. So which means this series is converge. Okay, so one more example, apply the ratio test. Okay, so like determining if this series is convergent, is converged. So n factorial over 100 to the n. Okay, so in this case, okay, so I have to say the ratio test work very well for some series contains like n factorial, yeah, or some 2 to the n, something like that. Okay, and then I write the an first. So the an is n factorial over 100 to the n. So I find a ratio, which is limit. So n plus 1 is n plus 1 factorial over 100 to n plus 1 over n factorial over 100 to the n. So yeah. Okay, and then I move all of the 100 to the n plus 1 to the bottom, and move all the factorial things to the top. So it's okay. So so it's m plus 1 factorial over n factorial, and then times, okay, so it's 100 to the n over 100 to the m plus 1. Okay, so we can cancel something here. So 100 to the n and 100 to the n plus 1. So this one we will get 1 over 100. And how about this term? So this term is like 1 times 2 times 3 to the n, and then times n plus 1. And for the bottom is 1 times 2 times 3 times n. So we can cancel the first n terms, and then you will only get n plus 1. So this limit will be the limit of n goes to infinity, absolute value. Yeah, don't forget the absolute value when we apply the ratio test. N plus 1 over 100. Okay, so we can see on the bottom is a finite number, and on the top it goes to infinity. So this limit goes to infinity, so which is greater than 1. Okay, so which means this series is divergent. Okay, so this is the ratio test. And then let's go to the root test. Okay, so the root test is if we have a series like summation of an, and then we can find the limit of the nth root of the absolute value of the nth term of a. So if we get this limit is some constant. If this constant is less than 1, then we can say this is absolute convergent. It's absolute convergent. And if L is greater than 1, which means it's divergent. And then if this L is equal to 1, the same as the root test, no conclusion. Okay, so let's go to the example. If we have the series is 3n over n plus 1 to the 2n. So for example, and then we can apply the root test to find the root, and then check this root is greater than 0 or less than 0, and then we get the convergence of this series. So I write this an first. So the an is the 3n over n plus 1 to the 2n. Okay, so I find the n root of the an. Okay, 3n over n plus 1 to the 2n. So the nth root is equivalent to 3n over n plus 1 2n. So the nth root is equivalent to take the power to 1 over n. Okay, so we can combine the power 2n and 1 over n here. So it's limit n goes to infinity, and then we can multiply 2n by 1 over n. So it's 3n over n plus 1 square. Okay, so I can just take the limit inside the parentheses. So it's limit n goes to infinity 3n over n plus 1 and then square. Okay, so for a limit inside, we know it's 3. So it's 3 squared, which is 9. So we get the root is 9, which is greater than 1. So which means this series is divergent. Okay, so this is a simple example for root test. Okay, so finally, I will give you some series, and then you can determine if the series is converged by finding a good method. So I mean, we have learned many methods to determine if a series is converged. I think we know the ratio test. Okay, so I just write down all of these tests. Okay, so you have, yeah, I just check my notes. Okay, so the first simple one is like the P series. And then the second one, I think we know we have the comparison test. And also we have some integral test. And then okay, so and some method we learned today is alternating series. Alternating series test, and then ratio test, and the root test. Okay, so I will give you some examples, and then you can choose a good method to find if a series is converged. Okay, so the first one is the summation of 2 to the k over n factorial, and it's from 1 to infinity. Okay, so which method will you use? Yeah, because we know usually we can see a n factorial on the bottom. So usually if we have some factorial in our series, we will pick the root test first. So I mean, in this case, I can write the an is 2 to the n over, okay, so it's 2 to the n over n factorial, and then an plus 1 is 2 to the n plus 1 over n plus 1. And then we take a ratio of an plus 1 and an, and then the n factorial will be cancelled out. I mean, only the last term will be in our limit, and then we can find a limit. So we can apply the ratio test if we see some factorial in our series. Okay, so let me go to the next example. So the next one is like a summation of -1 to the n, 8n over a over n plus 8. Okay, so for this one, because we have -1 to the n, so it's an alternating series. So I will first try the alternating series. I mean, we satisfy these two conditions. So I mean, Bn, it goes to 0 as n goes to infinity, and then the series Bn is decreasing. I mean, if we drop the -1 to the n, then we can say this series is converged by alternating series test. Okay, but what if, okay, so how about the series, I mean, I add an n here, and then what's the convergence of this series? I mean, because it's an 8n, so it doesn't satisfy these conditions of the alternating series. Okay, so for this one, do you remember conclusion comes from the definition of the convergence? I mean, there's a conclusion here. If the limit n goes to infinity, an, I mean, this limit does not go to 0, and then we can say the series n, the series an is divergent. So I mean, in this case, the alternating series test doesn't work. So we need to find some way to prove this series is divergent. So in this case, I just find, okay, so in this case, our an is -1 to the n, 8n over n plus 8. So we take a limit, n goes to infinity, -1 to the n, 8n over n plus 8. So, I mean, for the first term, so it's a product of these two limits. So the limit of the second term, it goes to 8. And then for the first term, it does not converge at all. Yeah, so which means this limit is not goes to 0. And then we can say this series is divergent. Okay, so some more examples. So what if our series is like sum of n cubed plus n squared over n5 plus n cubed plus 1. So 1 to infinity. Okay, so in this series, we can see there is a dominant term on both of the numerator and denominator. So, I mean, in this case, we can use the comparison test. So I can compare the convergence. We can compare this series to the series only contains the dominant term. So it's n cubed over n to the 5. So n is from 1 to infinity. So this one is 1 over n squared. Okay, so we can see this one, we apply the p series with p is equal to 2. So in this one is converge. And then we can say the convergence of this original series is the same as the convergence of this series. So which means this is converge. Okay, so the last example is find the summation of 1 over n times square root log n from 2 to infinity. Okay, so for this one, I tried, yeah, you can try the ratio test, and then you try the root test. I mean, it's really hard to find the ratio or find the nth root of this one. And also, it's not the alternating series. So I mean, because you have no -1 is oscillating. And also, you check this definition, the limit an, I mean, each term of the series will go to 0, but we cannot say it's converged. Okay, and then we go to a comparison test. I compare to the series like 1 over n, but I mean it's diverge. So I mean this series is always less than 1 over n. But the problem is the nature series is diverge. So we cannot determine the convergence of this series. And yeah, okay, so we have to use the integral test for this series. Yeah, because it's possible to us to find the integral of 1 over x times square root of log x dx. I mean, if you make a substitution, u is log x. Okay, so in this case, we will use the integral test. Okay, so yeah, that's all for today. Thank you for coming.